Example 8 basically references the warm-up exercise that we started the whole entire lesson with. And that particular question implied that whenever we have a repeating decimal or a non-terminating decimal, that it's basically a series in disguise. All right, and we're going to see that play out in this particular example. Write the decimal number 2.317 repeating, and it's just the 17 that's repeating, as a ratio of integers. Well, writing a number as a ratio of integers, that means it's a rational number. Rational numbers, when I'm looking at decimals, they either stop, they terminate, or they repeat. So I should be able to write this as a ratio. And it's probably not something that you've had to do before, but calculus, and specifically series, is going to help us figure out how to do that. And it's something that a calculator could do pretty easily. You know, like your math enter button, that's probably your friend. Yes, so we're going to function as our math enter button here in a second. Okay, so first of all, I want to rewrite this in a form that makes it obvious that it is, in fact, a series. So I'm going to break it up into its parts. And it's going to be sort of like whenever you first learned place value in whatever grade that was, like second or third grade. It's like this. I've got, did you see the screen just move for a second there? Okay, 2 plus, and now let's take that 3 digit. That 3 digit's in the tens place, so this is 3 over 10 plus, now I'm going to take the first 17 that's right here, right? Okay, so this 17, dang it, this 17 is over, well, what place value is that going to be? Let's see, this is, I've got basically 3 of those decimals. That's thousands place. I'm going to write that as 10 to the third. Okay, and then I would have another 17 here. I'd have another 17, and it's going to be, I would need to move that decimal place over 2 more places. If I'm at 10 to the third, it's actually 10 to the negative third. If I move that over 2 more places, that's going to be 10 to the fifth down in the bottom. Then I'd have another 17 over, I need to move it 2 more decimal places, 10 to the seventh, and then so on, right? I think that's enough terms to be able to see that it's definitely a series, an infinite series. And it's actually a geometric series, as we're about to see. But the problem is that the first couple of terms here messes everything up. So I'm going to set the first 2 terms aside. And the reason why it messes things up is because look at everything that's left over here. All of this stuff. All of this has stuff in common. Specifically, it has like that 17 that's in common all the way across the top. And the first 2 terms, they don't. And then the bottom, it looks like it just keeps multiplying by 10 to the second power, by 10 to the second power. And that is true, I guess, for the 10 that's on the bottom of this 3 right there. However, the 3 times something's not going to give us 17 and have a common ratio. So, like I said, we're just going to shove that stuff out to the front. And let's just go ahead and simplify it. We're looking for a ratio of integers, so I need to combine those 2 things. 2, in terms of tenths, would be 20 over 10. So 20 over 10 plus 3 over 10 is 23 over 10. So I've just simplified just that part right there. Boom. And now I'm going to write in summation notation the rest of the series. And it's going to be a geometric one. So plus, I have a sum, and I need a couple of things for this. I need my first term, and my first term is right here. It is 17 over 10 to the third. And then I need a common ratio. Well, what am I multiplying by? It's not 17 on the top because 17 stays the same. It's just something on the bottom. It is as 100. It's 10 squared, right? I'm multiplying by 100, I'm multiplying by 100, and so on. So my common ratio is 1 over 100 to the nth power. Okay, now look at it. Look at our common ratio here. Our common ratio, R, is equal to 1 over 100, which is absolutely less than 1, which means that this one converges. Not only does it converge, we have a sum to figure out what it converges to. And that sum is going to help me finish off this problem and rewrite this whole thing as one complete fraction. All right, so I'm going to bring down this 23 over 10 plus, and now let's write the sum of the infinite series. So it's the first term, which is 17 over, I'm going to write that as 1,000, over 1 minus the common ratio, which is 1 over 100. All right, now if you had to do this on the AP exam, which you won't, then that would be safe stoppable. But you know, the question is asking me for a ratio of integers. So let's just keep simplifying. Okay, so 23 over 10, you're not doing anything with that one. But I'm going to simplify the fraction that's on the bottom. So plus 17 over 1,000 over, I would have 100 over 100 for my 1, minus 1 over 100 gives me 99 over 100. Okay, and now I'm going to keep going. 23 over 10, and this is basically equal to 17 over 1,000 times, I take the reciprocal because I'm dividing by a fraction, 100 over 99, right? So now let's simplify here. We can cancel out a couple of zeros for sure. So, and I'm left with 17 times 1 on the top, and then 10 times 99 on the bottom. That's going to be easy enough to do. 23 over 10 plus 17 over 990. Whew. All right, now I have to add these two fractions, which means, of course, that I need a common denominator. Well, in common denominator, it can just be like, it's going to be this bigger number because 10 goes into 990. So to get the fraction on the left to have a bottom number of 990, we need to multiply the top and the bottom by 99. So I'll do that right over here in the margin. So it's 23 times 99. 9 times 3, 7. Carry 2. 18. Plus 2 more is 20. And then I'm multiplying by 9 again. So it's a 702. 2277. There you go. So this is 2277 over 990 plus 17 over 990. Come on, fix that. 990. So I need to add 17 to this. Okay, so that'd be 14. Carry the 1. That's a 9, I think. 79, yeah. And 2. Which means our final answer, 2294 over 990. Nice. A little bit faster than hitting math enter on your calculator for sure. But you know what? I'm curious. Let's check it. Let's make sure that this actually, all of this process makes sense here. Calling up the calculator. And I think that we had 2294, and divide that by division 990. Let's approximate this, and we should see our repeating decimal here. 2.317171717. We did it correctly. Okay. Example 9. Find the sum of the series, summation n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. Well, notice that this is set up to look like a geometric series. It's just that instead of having a number in there for the common ratio is a variable x. This is an example of what is called a power series. It gives us kind of a preview, a sneak preview of what's to come, like where the whole entire unit on series is basically headed. Okay, so let me flip back over here. And just in case you wanted to know what the heck this thing actually would look like. So this series, when we're looking at it, looks like this. N equals 0 to infinity of x to the n. If I were to plug in 0 there, I would have just 1. If I were to plug in 1, I would have x. If I were to plug in 2, I'd have x squared, x cubed, x to the 4th. You get it. Plus x to the nth, but in this case, you keep going after that, right? All the way to infinity. Well, all right, so this is sort of functioning just like a geometric series. And if we are assuming that our common ratio here, the absolute value, is less than 1, then that means that this thing is supposed to converge. All right, if it converges, we should be able to figure out what the sum is. The sum is equal to whatever the first term is. Well, we just wrote out our first term. It's right there. It's 1 over 1 minus the common ratio. So in other words, this is a function. A power series is a function. This f of x equaling summation from n equals 0 to infinity of x to the n, it is equal to the function 1 over 1 minus x. And you've graphed that before. You graph that function in, say, Algebra 1. It has an asymptote at, let's say it has an asymptote at 1. And also has a horizontal asymptote at 0, right? It's one that you could graph pretty easily. So it looks sort of like this. If I were going to graph this thing by hand, I have a vertical asymptote at 1. I've got a horizontal asymptote at 0. Can't see it though. All right, if I were to plug 0 in here for x, I would have 1, positive 1, which means it looks sort of, it's got to go there, I think. Right? And then this thing is a disco dancer, so it's going to be this other part that's over here. Okay, so what this particular question is referring to is the fact that this series will converge to this graph, but it's not going to do it everywhere. It's only going to do it over this particular domain, because anything outside of that domain, it's going to diverge. So it's only valid from -1, so it's the absolute value of x is less than 1, which means it's valid from -1 is less than x, which is less than positive 1. On my graph, it's this part right here. It doesn't work anywhere else. It only works right there on that little part. All right, I think that we have maybe one more. This one's a strange one. Show that the series from summation from n equals 1 to infinity, 1 over n times n plus 1 is convergent, and find its sum. All right, well, since that wanted to quit on me, I guess this is my technology telling me in some kind of way that's a good place to end this particular lesson. So we'll pick up that example 10 in the next one.